Welcome, everybody. Welcome to the eWater webinar for today. We're talking about modelling groundwater surface water interactions using eWater source. My name is Carl Daamen. I'm a principal hydrologist at eWater. My colleague Rachel Blakers, another hydrologist at eWater, will be talking for the second half of this webinar. Just before I get going with the topic of the day, I wanted to quickly cover some events that are happening with the eWater source model over the next short while. We have a training course in Brisbane on the 14th and 15th of June, which basically covers in a lot more detail what we're going to talk about very briefly in the webinar today. We have a source workshop on the 24th and 25th of August in Canberra, and we'll be requesting submissions for the workshop shortly, and just details for others who just would like to attend. There'll be a new timetable for training courses and webinars for the next 6 months that will come out shortly. And we're hoping to have a new production, well, we're not hoping, we're intending that there'll be a new production version of Source released in the next few months, and it'll have lots of new features, so keep your eyes open for that one. If there are any questions during the talk today, please type your question into the GoToWebinar question pane on the right of your screen. And we'll be dealing with most of the questions at the end, but if you have some points of clarification, we'll also look at those as we go through. Okay, so on to the day's webinar. We're talking about exploring the tools that are available in the source model for groundwater surface water interaction. And the context of these tools is that we want to model the effect of groundwater processes on river flow. So the source tool, groundwater tools, do not aim to provide any sort of groundwater resource assessment. It's more focused on groundwater influence on river flow. And in that regard, you could also, if you have a model, say like this one here, for a small river system, there might be several links within this model which you think have significant interaction with the groundwater system at the link. And what we're explaining today is how you can represent those sorts of interactions with the groundwater system. So we have a number of ways that we represent groundwater processes in source. We can lump groundwater processes into rainfall runoff models. And many rainfall runoff models have some groundwater component or a groundwater store in the model, in the rainfall runoff model. We can also input time series of water movement between the river and the groundwater system, and I'll talk some more about that in the upcoming slides. We have a toolkit, the GISWIT toolkit, which looks at near river floodplain groundwater processes in an analytical groundwater model, and I'll be talking a bit more about that and giving a live demo of that as we go through. There's a simple numerical groundwater model, and Rachel Blakers will talk about that. And finally, she's also going to talk a little bit about work we've done with source and comparing the source model against regional groundwater models. So on with my part of the presentation, the analytical tools for representation of interaction. You can input a groundwater flux, a direct groundwater surface water flux estimate time series into the model, and that time series you might have calculated yourself in a spreadsheet, or it might come out of a modflow model, and you can just plug it in directly into a link in source. You can also input a time series of groundwater heads that are relevant, or an average level of groundwater at the link in the model. And then the model calculates the gradient between the river and the groundwater for every time step and estimates the flux between as a result of that gradient. We also have, as I mentioned earlier, this floodplain water balance components tool, and I'm going to talk about the saturated connection model that uses these water balance components. So the components that are available are things like pumping, pumping from the groundwater system near the river, also evapotranspiration from vegetation on the floodplain, recharge from rainfall or from irrigation into the groundwater system on the floodplain. We have a description of infiltration from low points on the floodplain that are filled during an overbank flooding event, so that those ponds, if you like, might fill on the floodplain. You'll have some infiltration and some evaporation from those ponds. We can model that in source, and also the bank storage and a couple of other things. So I've got a list of those water balance components that can be added in on this slide here. Just remember, we're talking here about shallow, near river groundwater systems, and the things that we can represent are effects of floodplain inundation at low points on the floodplain, uptake of groundwater by vegetation, groundwater recharge from irrigation or rainfall, effects of groundwater extraction by pumps in unconfined and semi-confined groundwater systems, riverbank storage, diffuse recharge, or this low flow, sort of a background loss and gain. Is this, under low flow conditions, is this particular river a losing river or a gaining river? So I'm going to now step through a small live demonstration of how you might enter these features into a source model. And the features that I'm going to add into the model are groundwater pump, small irrigated area, an overbank feature that's a depression or a low point in the floodplain that might fill with water during high flow events, and this low flow loss, continual loss from the river, I will add in as well. All right, so I'll just reorganize my screens here so that we can move to a model. Here is a model I've just set up, very simple model. We're only looking at a single link. We've got an inflow node at the top, and I've already added in a flow time series into that inflow node, and a gauge at the bottom, and obviously the link between the two. Now, the first thing that you need to do when you're wanting to represent groundwater surface water interaction is to redefine this link to be of a storage routing type. When you've done that, you can then actually edit the link and the features in the link. So you double click on the link and it opens up the feature editor. Then you can then configure that link to meet your requirements. So I've got a couple of things I can add in here: the elevation of the link, the link length, and we want to add in a rating curve because we want to know for a given flow volume what the level of water will be in the river. So I'm just going to import that. Change your units if you need to. So this allows us to link the water level in the river to the flow volume coming down the river, which is what the model is. The model provides the volume of flow, and this rating curve then converts that to a water level in the river bed. We can then go down to the groundwater option here, and we can add a flux input or a heads input. model, which are the first ones I talked about. It's a time series of fluxes between the river and the groundwater system, or a time series of heads for the groundwater system alongside the river. We're going to add a saturated analytical model. Once we've added that model, we can then add our components of the model. So I'll add a point recharge. What happens here is that we give a location on our floodplain for the centroid of our irrigated area, and that becomes the source point of recharge in the system. So I'm just changing some of the parameters here of our groundwater system. And I want to put in a recharge here. I'm going to use units of megalitres a day. That's a lot more convenient for this particular example. So I'll add in a 0.5 megalitre a day recharge that will be entered into the model at that particular point on the floodplain. So just to show you how easy it is to add other bits and pieces, we can add an overbank, which is the low point in the floodplain, and I'll show you a bit more about that. We can add an unconfined pump, and we can disable this, or enable, sorry, this low flow transfer between the river and the groundwater system. Now I've set those all up, configured all of those in another model, so I'll just switch to that now. And we'll open up the groundwater link again. And you can see here that those different features. I just talk very briefly about the overbank here. When you're setting this up, you can edit the cross-section for the overbank. You define here a cross-section through this depression on the floodplain, and Source automatically calculates a level volume area relationship for that particular volume. Then I'll just cancel out of that. I'll just show you very briefly the unconfined pump example as well. Here I've set up a function which basically selects from the 2nd of January to the 29th of January as a period for pumping at 2 megalitres a day. Using a function like this provides you with a lot of flexibility in terms of what you can request of the model in terms of time series of fluxes. All right, so we've set our model up. You then configure it, which I've also done before. So, and then we run it. And what it's doing here is running a 30-year period. And now that's finished. I'll bring up the results manager. And we're mainly interested here, of course, in the Groundwater Surface Water link, the storage routing link. We've set up our active groundwater model, and there's a lot more under that tab that I could show, but won't take too much time on that today. I mainly want to show this groundwater flux. This is the flux from the river to the groundwater system. And the other thing I'll just show you is downstream flow and the upstream flow as recorded by the model. Now I've got all of these actually annotated a bit in another slide, so I'll switch back to my PowerPoint presentation. And you can see here, this is the total flow from the river to groundwater. And here we have a 30-year period, this flux plotted for 30 years. The peaks in the flux show the pumping in January. We put in that the pump was pumping at, I think it was 2 megalitres a day. So that's what's shown here. The spikes show that. There's also the daily groundwater recharge that is plotted here at -5 megalitres a day. That's because the recharge is actually causing a flux from the floodplain into the river. at half a megalitre a day. And then the recharge from the floodplain depressions are occurring irregularly, and you can see them along the bottom there when a high flow event comes down our river system. If we look at that in terms of upstream flow and downstream flow, this next figure shows the upstream flow as the green line and the downstream flow as the red line. And you can see that our groundwater system here is actually maintaining a low flow in the river through the dry periods, except in January's when the groundwater pump's turned on and it's sucking all the water out. That's you can see that along the zero line. If you look at the top of the peaks, you can see that sometimes the upstream flow is actually exceeding the downstream flow, and that's when the groundwater pump's turned on. The groundwater pump is actually sucking water out of the river system, so that the downstream end is showing less flow than the upstream end. All right, I think that's the end of my little example. We have a question. Can we show groundwater fluxes with extractions negative and recharge positive? Yeah, you certainly can. There's a lot of, the results manager has a lot of flexibility in terms of the way results are presented. I won't try to show it on the screen right now, but there's a feature that allows you to turn curves around. So you make your positives negative and your negatives positive. So that's quite easy to do within the results manager. Rightio. Well, that's me for now, but I'll just hand over to Rachel Blakers. But any more questions, please keep them coming, and we can answer more questions at the end of the presentation.
Thank you, Carl. I'm going to be discussing the numerical groundwater tool, and I'm going to start with a little bit of background theory and then do a live demo that shows is actually equivalent to the analytical model. I'll then finish up by talking briefly about a project comparing the numerical groundwater model in source with ModFlow. So the numerical and analytical tools have a very similar purpose. The numerical tool is designed to be easy to use and to capture the dominant stream aquifer interaction processes. It's intended to avoid the data and computational complexities that are usually associated with a full-blown 3D groundwater flow model. If you'd like to do a regional groundwater assessment, then you might like to look to linking a model such as ModFlow or FeedFlow with source. The numerical groundwater model is based on an explicit one-dimensional finite difference scheme. It has a representation of the saturated zone, which is based on the finite difference scheme. It calculates the heads in subsections or cross-sections parallel to the river reach, and then calculates the fluxes between each subsection and the river itself. So the user defines the spatial scale or the level of spatial discretization of the finite difference scheme. It also has a simple unsaturated zone representation, which is based on the Mean-Larsen formulation of the Green-Ampt equations, for some people who might be familiar with that. It models the processes of flood recharge, so that's ponded recharge on the ground surface, diffuse recharge and infiltration through the unsaturated zone to the groundwater table, pumping and injection, and evapotranspiration. The model, similarly to the analytical tool, assumes that the subsurface soil properties are homogeneous in our river reach. The numerical and analytical tools can be configured to produce equivalent solutions. The primary reason for introducing the numerical groundwater model is that the finite difference scheme provides a flexible and easily extensible framework if we want to introduce new functionality in the future. The other reason was that the analytical solution tends to slow down for very long simulation times, or if we have highly time-varying inputs, and that's to do with how it solves the analytical groundwater flow equations. However, the two tools don't have exactly the same functionality. And this table in the screen below just highlights some of the differences between the two models. The analytical toolbox allows you to input time series of fluxes or heads, which you might have calculated from a mod flow analysis, for example. We haven't duplicated that functionality in the numerical model. Both models do represent overbank flows, but a little differently. The analytical toolbox has explicit overbank features for ponded depressions in the floodplain, while the numerical tool at the moment doesn't have those overbank features, but it does represent flood infiltration as the stream flow rises and spills over the bank. However, it doesn't capture that ponding as water is pooled in some areas, low-lying areas of the floodplain. The numerical model has a concept of aquifer depth, which can be important. In the analytical tool, pumps will continue indefinitely, so there is no bottom to the aquifer. The numerical model also enables you to display groundwater heads, which is obviously critical if you'd like to calibrate your model to observed groundwater data. And we also have that simple unsaturated zone representation in the numerical tool. I'm now going to go to a live demo where I show how to construct the numerical groundwater model, and I'll go through this quite quickly because the process is very similar to the analytical tool that Carl has developed. And then I will show the results of the analytical tool and the numerical model combined. So I already have created a simple analytical groundwater model on this river link. The groundwater tools in source are typically defined on the scale of a river link rather than a regional scale. So on this river link, we have a constant inflow of 500 megalitres per day. This example is not meant to represent a real system. We're using it to just examine some of the features of the two tools. We've defined some properties for the subsurface, and we've also included one pump, which is located 1,000 metres from the stream. For this pump rate, we've defined it using a function. The function might look a little bit complicated, but all it is the pump is initially off. It then oscillates on and off for 6-month intervals for about 40 years, and then turns on for another 40 years at the end of the simulation. So it's not realistic. This is a 100-year simulation in total, but it shows the interesting behaviour of the two models. So I'm going to duplicate this section of the model. So I'll just copy and paste those nodes. I'm going to rename this link as Numerical for Numerical Groundwater Model. I'll go in and edit it. I'll delete the saturated analytical model, and I will create a new saturated numerical model. So in the first screen of the numerical model, we have 5 panes that we need to configure. The first one are the same common controls that we have for the analytical tool. So these are those general hydraulic properties of your aquifer. The second pane defines some, mainly relates to the parameters needed for the finite difference scheme. And on the third pane, we have infiltration parameters. So that represents the unsaturated zone. And below that, we have some properties for evaporation. And finally, we can select a cross-section. And this is the key thing that we need to do at the start of creating our numerical model. So this cross-section defines the geometry of the riverbed and the surrounding floodplain. I'm going to use one that I've already loaded in the model. I've shown it here. The key features of this are that we need to identify the left and right banks of the river, and we can also set some properties around Manning's End and slope. So I've selected that cross-section. I'm going to create a rating curve similarly to what Carl demonstrated for my stream. So this is so we can convert our stream flows to heads. And I'm just going to create that from the cross-section that I already defined, and it will be based on those manning and slope parameters that I mentioned earlier. So there is our cross-section. Now I'm going to set up the common controls using the same settings as what I did for the analytical tool. So we have a no-flow boundary at 5,000 meters, a specific yield of 20%. For the finite difference scheme, I'm going to use 20 divisions per bank, and importantly, I'm going to set an aquifer floor of minus 20 meters. This coordinate system is relevant to the cross-section I defined, which happens to have the ground surface, I think, being at about 7 meters from memory. I'll now select how we define the initial groundwater table heights, and I'm going to make them equal to the height of the river at time t equals 0. We don't actually need to configure much in the unsaturated zone model if we're not going to be modelling infiltration. But I'll just do a couple of things. I'll set my initial soil moisture to 20%, make sure my saturated soil moisture is higher than my initial, and I might just put some values in for the saturated hydraulic conductivity and average suction. These are parameters of the mean-Larsen equation, and we provide some guidance on how to define them and what they mean in the documentation. I won't set some evaporation properties. If we look at the model, we can, or right-click on the model name, we can see what types of components that we can add to the numerical tool. We can add diffuse sources, which represent things like rainfall or irrigation recharge. Direct diffuse sources, which, similarly to a diffuse source, are applied over an area, but they're injected directly into the aquifer rather than being applied to the to the soil surface. We have a pump and an injection bore, which is the opposite of a pump, and also observation bores for looking at groundwater heads at specific locations of interest. So I'm going to add a pump, and I'm going to define the pump rate to be the same function as what I used for the analytical model, and I'm going to make it the same distance from the river as for the analytical model. Now, because my coordinate system is a little different, that actually makes it 6,240 meters from the river, or in my coordinate system, which is 1,000 meters from the river. I'll also add an observation bore, and all we need to do here is set the distance that we would, or the position that we'd like it in our coordinate system. So I'm going to make one that is exactly on the location of the pump, and I'll add a couple of others. One is going to be almost on the riverbank. It's actually 2 meters from the riverbank itself, and one of them is going to be very near the no-flow boundary. So I'll go OK. And that's configured a very simple example of how to use the numerical tool. I have actually simulated this model previously, and I'm just going to pull up some results. So this is our results manager, and I've created a custom chart that looks at the stream aquifer flux for both the analytical and the numerical tools. As you would hope, they predict very similar results, and as you increase the number of subdivisions in the numerical model, you'd expect the difference between the two to become negligible, which it practically is in this example. Up to this point here, at about the year, 2100, this is where the groundwater levels have fallen to the point that we've hit the aquifer floor in the numerical model. So the pumping has been switched off. In the analytical model, it doesn't have a concept of aquifer depth. So it continues to pump, and the stream aquifer flux continues to increase. Here, a positive flux means a gain to the aquifer. For interest, here's the pump rate function that I defined. So you can see it oscillates for a few years, turns off, and then turns on, pumps at a constant rate for a few years. We have the flow upstream and downstream of the groundwater model, and you can see the impact of the pumping on that stream flow. And finally, we have the groundwater the observed groundwater heads at varying distances from the stream. So this red line here shows the groundwater head at the location of the pump, and you can see that it approaches the limit of minus 20 metres, which is the aquifer base depth. We also have in blue the groundwater table height right next to the river, and you can see that it is receiving recharge from the stream, and the effects of the pumping are smaller. So to finish up, this is just a very simple synthetic example to kind of show the features of the numerical tool and compare and contrast those analytical and numerical tools. To conclude, I wanted to, so before going on, I'll answer a couple of questions. The first one is, can we use river cross sections with negative x values so that the centre line is at 0 metres? And the answer is yes. So you can define a cross section using whatever reference point you want. So actually in my cross section, I think that, or maybe it stopped at 0, but there's no reason why you can't define a cross section that goes negative. It's possible that you have some low-lying areas that are below sea level, so that could be a realistic example. The next question is, are there any methods of automatic calibration of the parameters of the numerical and analytical groundwater models? Again, the answer is yes. These models are best calibrated using external tools. So Source has a command line interface that enables you to run it from a batch script or any other program that can interface via the command line. So for calibration of this model, I've used some of my own R programs, or other people might like to use PEST or other tools like that. And finally, can constituents be used with the numerical groundwater model? Currently, we don't have constituents included in that model. Okay, so to go on, we'll answer more questions at the end. I just wanted to briefly mention a comparison of the numerical model with ModFlow. So I did this work in collaboration with Daniel Partington, who's doing a larger project comparing Source, ModFlow, and Hydrogeosphere. The study area for this project is the Upper Macquarie Groundwater Management Area in New South Wales. This, the Upper Macquarie system consists of quite a productive, narrow alluvial aquifer, and there's a lot of groundwater pumping, surface water extractions, and there are strong surface groundwater interactions. Here I've just shown our selected river reach of the Macquarie. That's the black line. And in the top pane, we can see the locations of groundwater extraction bores either side of the river. And in the lower figure, we can see an indication of the groundwater head gradient along the river reach. For this study, we're interested in comparing the Source numerical model with ModFlow, and we wanted to be able to ignore the effects of error in the observed data. So the data in this area is very patchy and has a high degree of uncertainty. So for initial study, we just wanted to look at the behaviour of the Source model in perfect conditions, and future work will be to calibrate the model to the observed data itself. But for this example, we calibrated the Source numerical groundwater model to the groundwater heads predicted by ModFlow. Here's an example of our preliminary results. We're looking at groundwater heads at 200 metres from the stream for ModFlow and the Source model. As you can see, we have excellent agreement between the two models. As we move further from the river, the agreement between the two models declines. This is a time series of the two models at 800 metres. The Source model is in blue, where ModFlow is in red, and at 2.2 kilometres from the river. So there are two reasons for the poor fit between the two models as we move away from the river. The first one is that for this preliminary study, there are some general head boundary conditions in the ModFlow model that we actually didn't include in the Source model. So if we had included those fluxes, we would, of course, expect the Source model to show a closer fit to the ModFlow model. The other reason is that the Source model isn't designed to capture those regional groundwater flow effects and it is intended to represent those surface groundwater interactions close to the river. And so we would expect it to perform better closer to the river anyway. So to summarise, SOURCE offers a range of groundwater tools at varying spatial scales and complexities. And our idea is that SOURCE can provide a toolbox that users can select from to select a groundwater model that meets the needs of their project. We have everything from very simple losses and gains that we can add into our rainfall runoff models to the numerical and analytical tools, and we also have the capacity to link with 3D groundwater flow models. The primary purpose of the built-in groundwater tools in SOURCE is to improve the calibration of our rainfall runoff and river network models. We also want to allow the assessment of the impacts of surface and groundwater extractions so that we can perform conjunctive water resource management. So that concludes our webinar for today. We're now going to open up for further questions. If you would like further support in this area and you have a support and maintenance agreement, you can contact eWater at support@ewater.org.au. Alternatively, we do have this upcoming course in groundwater modelling using SOURCE in June in Brisbane. So our first question, which I'll direct to Carl, is how many floodplain features can be specified? Number of wells, number of irrigation areas, etc.
So I think with this question, we have the ability to model a large number of features. That we're not limited to small numbers. Obviously, there'd be a sort of a critical number above which you probably there wouldn't be much point in increasing the number of wells. So you might want to perhaps combine the effects if you had, say, more than 100 groundwater bores in your floodplain area. But yes, no, we're not particularly limited by numbers of features, no. The second question was, is the level of the river fixed for the entire reach based on the rating table, or is there a gradient on it? And does the groundwater pumping affect the river level? So yes, the level of the river is effectively fixed for the entire reach, representing, I guess, the average level across the reach. The groundwater pumping does indeed affect the river level because it reduces the volume of flow, and then the rating table will indicate the proportional drop in level that would be matched by that drop in flow volume. Over to you, Rachel.
So the next question is there a reference available to the GN1D model? Yes, there is. We have documentation available in both the SOURCE scientific reference guide of the underlying algorithms and also in the SOURCE user guide for how to use the user interface. There, I think there's also some information available online from a recent conference, the Australian Groundwater Conference, comparing the SOURCE numerical model and ModFlow. And the next question is, can each of the finite difference grids be assigned varying values for saturated hydraulic conductivity? At the moment, no. It assumes that we have constant subsurface properties throughout the reach. Is there an easy-to-use link to PEST, or do we need to set PEST up using text files, etc.? Yeah, so we don't have a graphical interface to PEST, so you would need to set it up as you normally do. Running SOURCE itself is very easy. You just call our command line executable with the SOURCE project name and the values of whichever parameters that you want to set, but we don't. You'd need to do your normal processes for interacting with PEST. The next question is, do you calibrate the ModFlow model, or was it a blind calibration comparison? So in that example I gave, the ModFlow model was originally developed as part of an SKM report. I think it was SKM, which is linked at the bottom of that slide that I presented. You will get these presentations in a link at the end of in a couple of days after the webinar. So that was also then recalibrated by Daniel Partington, but for the calibration of source to ModFlow, we were just we assumed that the ModFlow calibration was correct, and we just calibrated the source model to the existing ModFlow model. The next question is, regional groundwater flow inputs to the edge of the floodplain is identified as important to floodplain processes and e-watering. So does this mean that source is not suited to this purpose and one must use more complex methods? Okay, so we can import those boundary groundwater fluxes into the source model. But if you are looking at the details of those groundwater head variations far from the river, then I would suggest that you should use an alternative tool, such as ModFlow. If you are more interested in the impacts of those processes on the stream aquifer flux, then source is likely to be suitable. The final question is, are the groundwater options available in the source public version? So the answer to that is that I believe the Analytical tool is available in the source public version, which is freely available. The rainfall runoff models and some of those have groundwater losses for very simple, if you can call that, groundwater model simulations are also available. But at this stage, I believe the Numerical tool is only available in the source public beta version, which is a restricted access license. And the final question is, do groundwater models interact between reaches? So currently they don't automatically interact. It's something that we're looking at for future development. If those between reach interactions were important, you can, using the source expression editor, write your own functions to describe the flow between those regions. Okay, that concludes our webinar for today. We'll be sending out a link to the video from the webcast within a couple of days. And also the questions that we've answered during the webcast today will also provide answers to on our online forums. And thank you very much, everyone, for attending.